In this video, we're going to take a look at some of the ideas behind broomball. So I'm going to have you take notes on a separate sheet of paper because you don't have your notebook right now. We'll put that paper in your notebook tomorrow. So let's first define Newton's first law of motion. An object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction when experiencing no forces or balanced forces. So some things that are key here is same speed and same direction. In other words, same velocity. When experiencing no forces, which only really occurs when you're in deep, deep outer space, away from anything that might be acting on you or pushing on you, and away from any planets that might be exerting a gravitational force. Or balanced forces, meaning there are forces acting on you, but those forces are canceling each other out. So let's take a look at a little flow chart here in the next diagram. So here we're seeing a little flow chart. If forces are balanced, there are two possibilities that could be occurring. Possibility number one is the object is at rest, meaning its velocity is 0. And if the forces are balanced, it will also be experiencing no acceleration. So acceleration equals 0, and that means the object will stay at rest. And this is what would be the case for, say, a bowling ball. So if you want to do a little example here, we could have a bowling ball sitting on the ground. Let me draw that ground a little better there. So there are two forces acting on this bowling ball as it's sitting at rest on the ground. And one is the force of gravity. And I'm going to draw that in here. I'm going to use blue vectors for force, and I will consistently do that. So we'll call that force of gravity. And another force acting on this ball is the force of the table pushing up on it. And I'm going to draw these two forces equal lengths, indicating that they are equal in strength or magnitude. And this upward force acting on it is called the normal force. Okay, now these two forces are balanced, meaning that they are pointing in opposite directions and are equal strength, equal magnitude. So they're going to cancel each other out. And this bowling ball in this situation is going to stay at rest. Now, the other possibility is that the bowling ball is already in motion. So its velocity is not 0. The acceleration of it will still be 0 because there is no overall unbalanced force acting on it, trying to accelerate one way or another. So the result is that the object will stay in motion with the same speed and same direction. So let's go back to the bowling ball. So here we have a bowling ball, and I'm going to show that it's moving by drawing a velocity vector, labeling it v. And I can go back here and actually show that it's at rest by putting v equals 0 next to it. Okay, now it's moving that way. There is still this downward force of gravity acting, as drawn here, pointing down. And there is still the upward force of the ground pushing up on the ball. And we'll label that, again, F normal. So what other forces are present on the ball? It's moving with velocity to the right, but if we assume that there is no air resistance, or that the air resistance is negligible, meaning we can neglect it because it's so small, or ignore it, then we can say that these are the two forces acting on it. They're balanced, so the bowling ball will keep moving with this constant velocity forever. Now that's a kind of hypothetical idea, because we know everything that moves will eventually slow down, because in our experience usually there's some resistive force like friction acting on it. But if we could get rid of friction, we would find that the object goes on forever. And we'll take a look at some examples of that tomorrow. So this idea that objects at rest want to stay at rest, or objects in motion want to keep moving, is called inertia. It is defined as the resistance an object has to a change in its state of motion, and it is proportional to an object's mass. So I should have a apostrophe there. And this idea of proportional, so let's write it this way here. Inertia, and there's a symbol for proportional that I'll introduce now. We'll see it later. It looks like this. Kind of like a fishy, if you will, or part of a fish. And what it means is that if the mass of the object were doubled, its tendency to resist changes in its motion would also double. If the object's mass tripled, its resistance to changing its state of motion would also triple. So it would accelerate 3 times more slowly. And it also goes the other way. If the mass was halved, then it would have half the resistance to its changing its state of motion, meaning it would accelerate twice as fast. So we'll get into more of the mathematics about this in our next unit, but I wanted to introduce this because inertia is a property of the mass of the object. And let's define mass below. It means how much matter an object has, and it's measured in kilograms. And by matter we mean stuff. We mean atoms, we mean the particles that make up those atoms, and it's measured in units of kilograms. That's the SI, the International System or metric unit for it, with symbols kg. Alright, so let's get comfortable using blue for our definitions, black for our units, and I'm always putting the symbol in parentheses after the word, because that will tell you what you can write to represent that word. Okay, and in a later unit we'll talk about how we can figure out the mass of an object if we know its weight or things like that. Okay, so that's what I wanted to go over with you, and we'll talk later in class. So bring your questions with you to class if you have anything that you want to go over.